Okay, so we've went over what a true experiment is, and we've went over correlational studies, prospective cohort studies, retrospective case control studies, and simultaneous ecological studies. We've went over some study designs, which are cool, necessary details. But basically, what we're trying to accomplish with these study designs is generate good explanations, or at least tentative explanations. Proving an explanation can take a while, but before you can even start to try to prove something, you have to at least generate the guess, generate a hypothesis. And so, generating good hypotheses is an important skill in science, epidemiology, critical thinking in general. You could say there's a web of causality. What kind of explanations we care about, or what kind of explanations are useful, depends on our goals. Like, if we're in a murder trial, an explanation of a stabbing as, well, the murderer's tricep contracted, which caused his elbow angle to increase, causing his hand to go down, and the hand happened to grip a knife, and the knife was sharp, and it was made of steel with holes in edge, and the pressure caused by the edge of the blade separated some tissue, which caused a fissure in a large artery, and due to blood pressure, a lot of blood came out of the artery and it didn't clot, and so the guy bled to death. That is an explanation of a fatal stabbing. Aside from, like, physiology or surgery class, that's not a very interesting explanation, though. A courtroom would probably be more interested in the murderer's motive. Why did you stab that guy? Was it because you're just an evil psycho who hated him? Or was it self-defense? Was it okay? Or should you go possibly be executed or put in jail for the rest of your life? The first explanation about the muscle contraction and the properties of steel and blood vessels, that was a mechanical explanation. Whereas the second one, was it self-defense or did you just hate the guy, was a teleological explanation. First one was, how physically did it happen? The second one was, why? For what? What was the purpose of it? And sometimes we care about one of those, sometimes we care about the other, sometimes both. There are lots of different kinds of explanations, and which types of explanations are useful to us really depends on what our goal is. Like, if we're trying to decide whether someone should go to jail or if they're free, if they're okay and should not go to jail, the teleological explanation is useful to us, and the mechanical one is boring. Sometimes it's the other way around in other situations. But a lot of the time, what a useful explanation is use case specific. However, there are some general criteria for good explanations, or rather a list of features of bad explanations. In general, any explanation, or hypothesis, if we want to use science vocab, it has to be consistent. It can't contradict itself. Like, when we get to liar paradoxes, stuff ties itself in knots. We don't like contradictions. Law of non-contradiction. So it shouldn't contradict itself. Also, it shouldn't be circular. A circular explanation might be true, but they're not very useful. They're tautological. Like, if I ask, why was the man murdered? And someone gives the explanation, because he was stabbed. Okay, yes, that's technically true. But it's circular. He was murdered because he was stabbed doesn't really give me much information. Who murdered him and why might have been what I cared about. He was murdered because he was stabbed. It's almost circular. It just doesn't really give me much. Also, aside from not being circular, explanations generally shouldn't be vague or ambiguous. Unless you mean them to be. But you should try to make sure that they're only vague or ambiguous if you want them to be. A lot of the times, explanations are vague or ambiguous not on purpose. And that reduces their usefulness, a lot like a circular explanation. And generally, a explanation shouldn't conflict with observable facts. Like observable facts and theories. Like, if I asked, why was the guy murdered? And someone said, because he walked in front of a stray cat on a Thursday. Well, I don't have much data saying that walking in front of a stray cat on a Thursday is a fatal event. Saying that walking in front of the cat caused his death conflicts with accepted theories and observable facts of biology. So that's a crappy explanation. Ideally, an explanation, if we want to elevate it to the level of a theory, or even a good hypothesis, ideally that explanation would make predictions about the future that turn out to be correct. If it makes some predictions that are correct, we'll trust it more in its other predictions. And then the most important one. An explanation has to be falsifiable. What does that mean? Well, it sort of goes along with making predictions. For a theory to make a prediction, the world would have to look one way in the future, if the theory's right, and look another way in the future if the theory's wrong. Like, if it says X will happen, well, I just wait for the future and look for X. If X does happen, theory's probably right. If X doesn't happen, the theory's probably wrong. The world looks different and by that difference, we could make an inference that the theory is correct or incorrect. What we have to watch out for is explanations that don't make predictions, that aren't falsifiable, that are just not testable. They might be right, but we would have no way of knowing if they're right or not. no way of knowing if they're right or not, happens when the world would look exactly the same in a situation where they're right as a situation where they're wrong. And that's a lot of words, so let's go with an example. Let's say two theories of what causes heart disease. One of these is going to be easily falsifiable. One of these is going to be not so falsifiable. Maybe a sedentary lifestyle, not exercising, causes heart disease. Well, we can investigate that. Find a bunch of people who don't exercise, watch them for a long time, see if they develop more heart disease than people who do exercise a lot. Or we could go to the hospital, go to the department with all the people with heart disease, and ask about past exercise habits. Did these heart disease people exercise less than average people? We can do some correlational studies to get a feel for whether or not there's a good association, possibly even an A causes B1, between heart disease and not exercising. We can work with that. Now, the other hypothesis. Sins in your past lives cause heart disease. It's a proposition. It could be true. It could be false. The problem is testing it. Well, just test it the same way you tested sedentary lifestyle. Okay, so we've find a bunch of people who are sinners in this life, and then watch them into their next life and see if they have heart disease in their next life. Perfectly good prospective cohort study. Or we look at people in this people right now who have heart disease, and we give them a survey. Do you have heart disease? Yes or no? Have you had a past life? Yes or no? In that past life, were you a sinner? Yes or no? Okay, I'm good on the first question. I know whether I have heart disease or not. But how do I know whether I had a past life? And what's your definition of sin anyway? We can't really get data on that. Pretty much no one can finish that survey. And we have a really hard time tracking people in their future reincarnations. We just can't get... People can't fill out the survey in the case control study. We can't keep track of people after death and into their next lives in the cohort study. We just can't get data on this. And so, to us, the world looks exactly the same, or in a situation where past life sins cause heart disease is true, and in a situation where past life sins cause heart disease is false. And so it might be true, it might be false, it's a proposition, but we have no ability to figure out whether it's true or false. It's not falsifiable or not testable. A non-testable hypothesis could be true. It's just useless to us because we can't figure out if it really is true or not. Of course, the line between testable and not testable does change over time. Like, if we went back to the days of Galileo and asked scientific questions about nuclear physics, to him they would have been not testable at all. The technology just did not exist to have particle accelerators and smash atoms and do nuclear particle physics experiments. The technology just wasn't there. So he would have said, yeah, your hypothesis might be true, might be false, but it's not testable. Hundreds of years later, the technology improved, and now those kind of hypotheses are testable. Maybe at some point in the future, we will be able to track people after death and into their next lives, or or look up people's past life experiences. I don't see how that's going to happen, but I don't know. Technology can do crazy things sometimes. Maybe those hypotheses would become testable, but they are nowhere near testable right now. And so for the time being, the past life sins cause heart disease hypothesis is sort of useless. It's not testable. Whereas the lack of exercises causes heart disease hypothesis, that one we can test with today's technology. So that hypothesis being testable is possibly useful. And picking good explanations to research further and do correlational studies and real experiments on is important. Picking your explanation is the first step in doing science. If you pick good explanations, your science might be useful. Whereas if you pick bad explanations, you might not be able to test them at all, or sometimes they're not useful explanations. He died because he was stabbed. Yes, we know that. That's not what we care about. Deciding what hypothesis you're going to try to investigate is the foundation of science. And at that foundational level is where critical thinking is most important. Usually when we think of science today, we think of a lot of technology, lab equipment, technical training, technical skill, a lot of technique. That technique is logically subsequent to episteme. The first, most foundational step in science is framing good questions and constructing useful experiments based on testable explanations and solid syllogisms where the data will actually bring us to new conclusions reliably. If you lack that episteme or just rush through that step, then you end up with people with lab coats and beakers, and it looks like they're doing science, but they're just sort of wasting time with fancy materials. Critical thinking, or having solid episteme, is foundational to getting much done with the technical prowess, the technique of modern science. And for us as normal people and critical thinkers, it's important to keep that in mind because, especially in the last century, science has got more and more and more focused on the technique. And that's fine. Technique's important, but you do need both. And if you watch Jurassic Park, you also need phronesis. Just because you could make a T-Rex doesn't mean you should. It might eat you. Phronesis, common sense, is probably the hardest one to teach. Episteme, critical thinking is, at least a course on critical thinking is mostly episteme. It's on the borderline of teachable or not. Techne is easier to teach. It's, I hope, it's most of what people learn in school. But hopefully, us as critical thinkers will be in a cutting edge, maybe even leadership position because of our competitive advantage of being especially good at interpreting data and forming useful hypotheses and figuring out how one would test explanations. And then the scientific technicians can do some lab work. But whether their work is productive or not is largely determined by the solidity of their epistemic foundation, the critical thinking stuff that we've just went over. And wow, now we've gotten from ancient Greece to knowing how to do science. You've gotten through pretty much the intellectual history of the world. Good job, guys. I'll talk to you again soon.